All right, so let's go. So welcome to this third part of RL for Jim DonkeyCar. And of course I will start with a recap of what has been done so far. And today, so the agenda of today is threefold. So first do a recap and then see how we can do experiment handling and tracking. And then also I will show you also the details, the small details for the secret sauce for having a fast racer and also learning to race in just hours and not days. So the first thing we're going to do is do a recap of what has been done so far. And in case you didn't see the first parts, you can always go to my YouTube channel. There will be the replay of the different live in there. And all the code and models will be open source also. So if you were not there last time, you can just go to my GitHub, search for Jim DonkeyCar 1, and in releases, you will have, no, not the one. In this repo, you search for autoencoder, so for DonkeyCar, and in releases, here you will have, for instance, the models and other links useful for today. So first thing first, what we're going to do is recap what we did so far. So what we did so far was, of course, installing the DonkeyCar and simulator, which is this one, doing some tweaks in the environment, playing with the environment. And once we did that, we wanted to learn to train an agent to race. So what we did is, instead of learning directly from pixels, is we learn intermediate representation using augmented autoencoder. And so last time what we did was actually collecting data, training the autoencoder, and testing it and writing a wrapper so we can actually use a pre-trained autoencoder in the RL training. And we started some RL training, but it didn't go so well, and I will tell you more about that, of why it didn't work so well. So if you didn't already, I will restart. Let's start from here. So in a folder, best is to have, so live 2, you will have 3 repository. One is the augmented autoencoder repo, and the branch is fit live twitch 2. Here, fit live twitch 2. You can see in the pull requests. So to see the edits we did. So what did we do? We mainly wrote the wrapper. We wrote some debugging script, and we added also a speed as input for our model. And the next things we did was also train the autoencoder. Like if you see in log, in dataset, there will be many images that we collected using record-data.python. And we can actually open this script. So here, record-data.python. What the script did was mainly do a loop. Let me here. Do a loop and collect the images, and we were driving it with a keyboard. And once we have saved all the images, what we did was to pre-train an autoencoder and test it. And then the autoencoder is saved in logs, and here there will be the different autoencoder. So for everyone to have the same autoencoder, I also uploaded the model here. I uploaded the dataset that was used to train it, and it was used for 400 epoch with, I think, a batch size of 8 and the default hyperparameters otherwise. And you can directly download that pre-trained autoencoder. No, this one. You can download it, and we can copy it here in the log. So it's in here, autoencoder mountain, and we can copy it here. So that's one thing. And of course, this repo is a package, so you can install it if you didn't install it already. So this repo is all about the autoencoder, and it's in there. Next thing is, okay. So next repo that we have in it is the Gym DonkeyCar, which is the code doing the glue code between the simulator and the RL agent. So it's the environment code. And this one is again available on here on my GitHub. You can directly go for it. And the branch we will be using, Gym DonkeyCar, is called, in fact, it's called Fit Twitch 3, like it's the part 3 of Twitch. And we will see what's inside it. Let's do a pull request to our own repo. What's changed in it? It's something that I started also to do a pull request to the original repo. What is changed is mainly different things. One thing is we have more config variable that we can change, notably the steering limit and the min and max throttle. That will be quite useful for RL training. And then we added also from last time some fixes for deciding when the model stops. So if the car is too slow for a too long time, then we stop it also. And the other important thing we did, that at least in that repo, and I will go back to it, is adjust a bit the reward function, and we will adjust it again. But mainly, what I did was normalizing it, but we will come back to that one. And the last repo that we have in it, it's called, so if you go back, it's called the RL baseline zoo. You can just search for RL zoo, and it will be one of the top one. And we are on the branch prepare Twitch live 3, fit Twitch. Part 3, yes. And what's mainly in there is some specific code for the DonkeyCar, and we will go back to it afterward. All right, so far so good. No question, no remark. All clear, perfect. So let's plug everything first and see how it goes. So what we are going to mainly use today is in fact the RL zoo, and we will see how what hyperparameter we can change, how we can run an experiment, and other things like that. So let's go in it and open the term. Let's open it. So if you go to hyperparameter tqc.yaml, that's mainly where we're going to do things. And I will remove what is not needed so far, and I will go into it. So here, how it works is for each environment, we will have a set of non-default hyperparameter that we want to change, and we can directly specify it there. We can also specify callbacks. So callbacks are quite useful if you want to log additional data, and that's why we're going to see also today how to log the lap time with a callback. We can also have callback, and this is also a very useful one to do parallel training. So we This one, I will dig a little more into it. It's at the same time that it's collecting data, the model is also training in a separate thread, and that allows to also save quite some time. So you don't need to wait for the model to train. It's directly training in a separate thread. And here we also activated normalization. So normalization is because the output of the autoencoder is not necessarily normalized, and if you want to make the training faster, you should definitely normalize. So we mainly normalize the observation. We could also normalize the reward, but for now we were not going to do that. And we specify different wrappers. So as we saw last time, if we don't specify wrapper, what will happen is we will feed directly the image as input to the agent, and it will take quite a long time to train. It will fill up your RAM, and yeah, basically the wrapper will allow you here. The autoencoder wrapper is from the package I just showed just before. Will be the one responsible for encoding the image into a small vector. And here the time limit wrapper is because we want our agent to have a more diverse training set. We want, like, if we would not put a max episode time step, what would happen is that it will only see at some point laps that are not first laps, and we want our agent to be good at the first lap and also at the next laps. So that's why we have a time limit here. So it's basically a timeout. And this is useful for training, but for testing, we will actually remove it manually because when we want to race, we don't want the model to stop after a certain time step. And then there's the budget. So how long do you want to train your agent? And different hyperparameter specific. Mainly here you have the policy network size. You have the learning rate, the buffer size, so how many transition do you keep, how many steps do you keep in memory for training, and it will be a rolling buffer. Gamma is a discounted factor, so it tells you should you privilege the short-term reward or the long-term reward, and it has also an effect on that. So next we can do two things. We can just launch everything and see how things are done, and then I will show you the hyperparameter, so the meta-parameter study I did, so to see the influence of the many things you can change in the environment. And to actually do the training, because we use the callback, because we use the autoencoder wrapper, and if we go back to here, autoencoder, and to the wrapper, we see that we need to provide the autoencoder path. And that's the first thing we're going to do is, so we are, let me open the bigger terminal. So we obviously start the simulator. I will set it to time scale of 4, so it's going to train also faster. I'm going in the RLZoo, not that one, directory. And here the first thing is I'm going to export the path to where is the to the autoencoder, and it needs to be the absolute path. Here, so I already have it saved, so I will just reuse it. And next things we need to do is called Python train, then the algorithm we are using, which is here TQC for truncated quantile critics. The environment, which is the same ID as here, so Donkey Mountain Track version 0. We're going to say we don't want to evaluate because we don't have a separate evaluation environment. And that's something I will also show you right now, is how to handle experiment, and we will for that use weight and biases. So weight and biases is directly integrated with the RLZoo, and for that you need to provide the project name, and here it will be Donkey Live for the live demo. And you need to specify that you want to track it. In addition to that, it's also a good practice to here say we want to save checkpoints, let's say every 25,000 steps. Because if our model fluctuates in terms of performance, then we would like to know that. Let's see, and I will just, for now, I will just launch everything and show you how things are going. And here it's, what's missing is eval frequency. So if you want to see it big on the screen, it looks like that. Okay, so what's going to happen is here. So it's going to start training the agent. And here we didn't touch the environment, so you will see something, yeah. It won't learn as good as it should be, but it will still start learning. And the other thing that we know is we have here, if we click on the URL, and I will make this project, in fact, public, so you can also access it. Here, I will make it public, and let me send it in the Twitch. Okay, and normally as soon as it starts, you will start to see some metrics. Here we go. Let me send it here. Okay, so here we go. I wrote it in the chat, the direct URL, but you could also just go directly to Weight and Biases a Raffin and /donkey live. I'm just going to do something to make everything looks better, which is I changed the x-axis not to step but to global step, which is the number of interactions with the environment. I will remove that section because it's not interesting, and we will start to see what's in there. So here we have the mean episode reward. Mean episode reward is here. You have the mean length. So the idea is here we want our agent to not fail to stay on the track and not bump into anything. And that's what the mean length of the episode will tell us about it. The FPS is just how fast are we with the environment. And in train, you will have different information about training. The learning rate is constant. The standard deviation will normally decrease over time, and you have different losses. And all those data come from, in fact, the integration with TensorBoard. The other interesting part is that in the config, all the config that is saved by the zoo is also saved here in Weight and Bias. And for instance, if, I don't know, I wanted to know what was the network I use, I could directly check and go for it. Okay, and another thing I also directly added the lap time in the callback. And in fact, that's what we are going to code right now, which is adding additional data to this board. Or maybe write me in the chat if you prefer that we do that, or I can also go more into the details of what hyperparameters you can change in the environment and that we are going to change. So there's a 404 error. Normally it should be public. Let me try in a private window. It should work. In a private window it works, so Same here. Okay, that's weird. Actually, yeah, this one gives a 404 error. DonkeyCar Live. Oh yeah. Sorry. So the real URL is Donkey Live. Sorry. So it's Donkey Live here and not DonkeyCar Live. Okay, now it works. Perfect. So this run is directly running on my computer, but you can follow it live, and you can follow. So here the lap time, you see it's around 30 seconds, and we can in fact go back to it and see how it's doing. So it's already finishing a lap, but it's not really fast. So with a fully trained agent, so in 1 hour you can reach around 20 seconds, and with even more training, you can go below 90 seconds. So my fastest agent so far is does laps around 18.5. And we will actually see how do we improve that. But let's continue with weight and biases. So I will also send you another link, which is also public, this one, which is, so you just put DonkeyCar, and here you will have all the runs that I did in preparation of that live. And this one should also work. And it contains so many runs. And the idea with all those runs is you can compare them quickly. You can filter. You can filter, you can group by, I don't know, probably I can group by, for instance, the discount factor. I can group by other, by the max cross entropy error that I, cross track error that I used for the track. So there's many things you can change. And you can also group them, filter, and what I did and what I will also dive into is I created a report. So if you go in the report here, and I compared all the different hyperparameters that you can change, and it's still ongoing. So as a disclaimer, as every run is several hours, I didn't have the time to do several runs. But usually the runs are quite consistent, so even though I'm doing only one run, if the difference between, for instance here, it's with or without history is quite, if the difference is big enough, then usually if you repeat the experiment, you will still get the same result. But as a disclaimer, normally I should do it much more quantitative, so at least do 5 runs before drawing any conclusion. But for instance, if you look at the network size, quickly here you can see that between a big network and a small network there's a huge difference, and I probably don't need to run it more to see that there's a huge difference in here. Okay, so this is the next part we're going to see, which is actually the interesting part, which is what matters when you train the RL agent. But before doing that, I just want to show how you can add additional data to your board. And for that, we're just going to go in the zoo. I'm going to go in here in utils, callbacks, and we are going to rewrite the lap time callback. So I'm going to delete that. And what we're going to write is a callback that every time there's a new lap, it will publish it. It will publish it, and so we can see it here. So if you want to write callback, the best thing is to look at the documentation. So you go, we are using stable baseline 3 library. So there's a lot of documentation about what is a callback, which is basically something that is called at every step that allow you to interact with the model, with the environment, and also log additional data or do additional things like saving a checkpoint is done using a callback, or evaluating the agent is done using a callback. And here we are also most interested by the TensorBoard integration, and we go to directly accessing the summary writer, because that's what we're going to do, is add a new value to TensorBoard. So I'm just going to copy paste this code, so directly accessing the summary writer, and we're going to modify it to fit on it. So the name here is lab time callback. And we are going to log as soon as we can. And what we want is a lab count to check if we need to log additional things or not. This TensorBoard formatter line is mainly to retrieve TensorBoard writer. It's not really important how it's done. And what we're going to do is on every step we're going to check the lab count, which is so for that we can directly access in the locals. We have access to the info from the environment, and the info from the environment we want to access. We only have one environment, and we are accessing the first key. And what we want is lab time, and for that to know which key exactly is here, we go to the environment. So Jim DonkeyCar in env in Donkey Sim, and I think it's called a new lab time, and it will be saved. So lab count, last lab time, yeah. So info, in the info, there's those two that we are interested in, which is a lab count. Lab count is this one, and lab time is last lab time. And what we're going to do is, if our current lab count is not the same as lab count, and also our lab time is bigger than 0, because what's going to happen is at every reset the lab count will be reset, and we may have something different. We're just going to I think it's called write value. Let's see, if we go to stable baseline 3, to common logger, and to the TensorBoard logger, for a scalar type it's called add scalar, and so we need a key, a value, and what is the time step we want to add it. So we're going to add a scalar which is called lab, so time in the time/lab time, and the value will be actually the lab time here. One thing we can do also is if the lab count is just 1, so it's the first lab, we can also compare first lab. Here, first lab time. Because if you go back to our study, here you can see, you can see in the lab time there's a lot of spikes, and all those spikes in fact are for every time we restart and we do the first lab will be much slower than the second labs. So what we can do is record everything, and also record separately the first lab and maybe the second lab's time or more labs time. and that we can do here, else we can second that time. So basically what we do is we write a key, which is in the namespace time, we write the lap time, and for the number of time step that we retrieve directly using the callback. And then to use a callback, we just normally add it here, so it's directly, it's already there, it's utils.callback and then the name of it, and we could pass parameters, but here we don't have any parameters, so we just add it here. And in fact, our training is going more well, and you can directly see it in Donkey Live. Here the lap time is slowly going down. I'm just going to also rescale it because we know we're not going to reach 0, so the minimum access will be that one, and maximum will be 35 seconds. Okay, and we need to use also global step. So global step tells you how many steps in the environment we have, but we could also have a relative time. So here after 15 minutes, we already are below 23, 24 seconds. I'm going to keep it running, and then now we're going to see what we can improve, what we can change. And for that, I invite you to go to the study that I will post here, which is in fact a bit all the secret ingredients for making the training fast and having a fast car. Is there any question, by the way? No questions, so I assume it's fine. So there's many things we can change to make the training faster or better. And I'm going to not go into every detail, but the most important ones. So the first thing is called history. So what we did last time was just feed the current encoded image, the current speed, and hope that the agent would learn. The problem is we didn't give the current steering position, and there might be some time delay because the simulator is asynchronous, it's not waiting for us, and so the current observation may not correspond, may be lagging a bit behind, or can you, oh yeah, sorry. Let me arrange that here. So normally you should be able to see again. No, wait. Changed to the wrong one. Okay. So that's how it looked like. Perfect. And in fact, most of that code you can find it already in the documentation of stable baseline. And this is not debugged, but I think it should be fine. I can actually check later and debug it later, but it should be fine. Any other question or remark or things that were hidden by my screen, on my screen? I would be curious to know a bit more on how you choose a reinforcement learning algorithm, or in general, how you think about experimenting and tuning hyperparameters for RL. So that's a very good question. And for that, well, I did, well, you can go to SB3 documentation. And in the tips and tricks, there's already quite something about, well, RL experimentation in general. but also which algorithm should you choose. And I did also a video on YouTube for all those tips and tricks. And for instance, here, which algorithm should you choose? And here, mainly the different thing you need to think of is both what action space do you have. So, what action space do you have? Is it continuous or discrete? And are you aiming at sample efficiency or speed? Speed in the sense whole clock time. So if you can have many simulation in parallel, then you can go for algorithm like PPO or A2C, which are, or even like evolutionary algorithm. But if you need to be sample efficient, which is our case here, because we can have only one robot, we could have multiple robots, but then they will collide and it will make us. I tried so far and it was not so successful. Best would here currently, and it works quite well also with those algorithms in terms of performance for continuous control. So, and in fact, that's part of comparing algorithm, which I did not do so far. I'm currently using TQC because it's a good default with good default hyperparameters that work on many different environments. So that's also why I chose it. And here, in the documentation, I go back, I explain a bit also what you should choose. How do you tune hyperparameters? Well, if you can, best is to obviously tune them automatically, and that's what, if you go in the RL zoo, that's what you can do also automatically. If you search for tuning, there's already hyperparameter tuning integrated in it. The problem is it won't work so well with the DonkeyCar because each run needs 1 hour or more. So usually what I do is I reuse hyperparameters that work for other environments, and that's what we have in the zoo. We have already lots of tuned hyperparameters for many different environments. And in fact, I reuse the one for the bullet environment mainly. I use those one, and then you can do a small study on key hyperparameters. And in fact, that's what I want to talk about now, in addition to the history. It's what hyperparameters are usually the most important to tune. So if you take a look, in fact, at what's in tqc.yaml, and you look at what's already in there, what is changed compared to the default. So buffer size is slightly smaller than the default. Usually buffer size, as long as it's big enough, doesn't have much importance. If it's too big, the problem is the new data will be less likely to be sampled, and so you won't improve your progress will be slower. And if it's too small, then your performance will also vary a lot because it will unlearn things. Then all those are default, and then discount factor, I'm going actually to talk a bit more about it. This SDE, so state-dependent exploration, is all about the exploration, and here it's a method I worked on for robotics. So it's really meant for robotics to have a smoother exploration, to directly also train on real robots, and you can search for the paper. It's called Smooth Exploration for Robotic Reinforcement Learning. Or search for my name on Google Scholar and you will find it. And the name of the method is called Generalized State-Dependent Exploration, or GSD for short. So the main ones usually to tune is the learning rate, which if it's too small, it will also learn too slowly. But if it's too high, it will also fluctuate or even diverge. The network size also is quite something important to tune. Usually having something big enough. If it's too big, the problem, it will be too slow to train. If it's too small, there won't be enough capacity to learn the correct value function or learn the correct policy, and it will underperform. And the last, well, one of the main one is the discount factor to choose between whether we want to privilege immediate rewards or long-term rewards. If you privilege long-term rewards, you may have side effects, and yes, that's the one of Archive. Archive is almost the latest version, but it's I think it's enough updated. And yeah. Okay, so let's start. So okay, now our agent after some time is already below 22 seconds lap time. And let's dive into well. So as I say, history wrapper is quite important because it will allow you to deal with time delays, and it will also give the agent about information about the previous steering, the previous action that was taken. And the history wrapper is already included in the zoo. If you go to utils, let's go to utils. And wrapper, and you search for history wrapper, not the tick one here. What it mainly do, it's stack packs observation and action to give an history to the agent. So it's usually a very good competitor to recurrent neural network and other things like that. So to have a small memory, but also to handle time delays. Because with time delays, you may break Markov assumption, and that may hinder training. All right. So what it does is mainly, it just stack an observation, the history, and the last observation and the last actions, and that's what mostly is done. So we concatenate the observation history and the action history, and we have a certain horizon. So usually just giving an horizon of 2 improve a lot the performance for when you have time delays, or in our case here, when we need to know about the previous action. And using that history, although you also to later have some other cost like smoothness, because if you want the action to output smooth action, it needs to know about the previous action. If you don't give this previous action, then you cannot also enforce smoothness. Okay, so that's the history. Next things we can change also is the limits of our action space. So the max steering. So currently I think it's between -1 and 1. And the throttle limits, which is currently I think between 0 and 1. The thing is, if we give too much freedom for our agent, it will also take much longer to learn, and it will probably underperform. And that's what you can see here in the small run I did. If I give too much freedom here, like between -0.8 and 0.8, so the max limit is -1 and 1, it still learns, but it clearly learns slower than if I give smaller limits. And also by limiting the steering, max steering, you will enforce more smoothness. And we can in fact compare, let me edit that, so we can, okay. So we can actually not only see it in terms of max time steps, but also in relative time. So here in 1 hour, after 1 hour, the experiment was around 20-second lap time, whereas the one with more freedom was still around 21 lap time after 1 hour. So we have almost 1 second of difference of lap time after 1 hour between the two. Okay. And here, we can see. So that's one thing we can change. And this is what I have if you go to the environment to DonkeyCar donkey env. You have the config, and in the config, that's all what we can change. We can change the max cross-tracked error. So cross-tracked error is you take the center of the track and you see how far we are from it, and we define a max distance from that line. The thing is, if we set it too small, then we would just learn to follow the center line, which is not the optimal, of course, way of racing. If we set it too high, then it will be harder to learn, and it will take longer to learn because it will be less penalized for being far away or being against the wall. And here we have the limits we can also directly change in the config. So those values, we can change them by passing a config here, config dictionary as input. And the good news is we can directly pass that via the RLZoo. I'm going to stop this training now because I would like actually to start integrating the different tweaks. So what happens when you stop training, it will save automatically. You can kill it before the end of the budget and it will automatically save it. And it will tell you in which folder it is saved. It will also save all the hyperparameters and changes in the environment that you did. So if you go to logs, TQC and the last environment, if you go to config, we have all the hyperparameter we used to train it. We have the normalization file which is saved here. We have the different checkpoints. And inside each checkpoint, we have the weights of the policy and other variables for continuing training. And in the argument here, it's all the argument we pass to the script. And for instance, where is it? The save frequency. And soon there will be what we call keyword argument. Here currently we pass nothing to the environment, but we will change the things, and that's what we're going to do right now. So we're just going to reuse the same thing. I'm just quickly going to debug the max callback, max lap time callback. Yeah. Okay, it didn't work because we need to pass a TensorBoard log. Okay, this will be done automatically when we log everything with weight and biases. Okay, it looks like it may work. Okay. So to pass additional hyperparameters, we're just going to pass to set env keyword argument. And here we want to pass a different config. So in the config, it will be a dictionary. And let me go back to the environment so we can see actually what we can change. We want to change the max crosstalk error. So currently it's just 8. We want to change the steering limit. So I will show you later, but usually 0.5 is a good start. On some environment, it's not enough because the turns are sharper and you need to set it to 0.8 or even 1. But for the mountain trike, 0.5 work quite well. Next things we want to change is the throttle max and throttle min. So in practice, the real max throttle is 1. But the thing is, if we set it to a higher value, it will be anyway clipped by the simulator. But if we set it by a higher value, it's easier for the RL agent to actually sample the highest throttle and to be at the limit of the action space. And the throttle min, currently we cannot go backward, but we can allow to go backward a little bit. So if we go slightly faster, we can go backward. That's it. And for fun, we can also, I think there's a car config we can change. If you go to, again, Gym Sim, and you go up, it's called car config. I think it's car config. Yes. And in the car config, so we can say car config is a dict. And let's just say that the car name here is RL test. Okay, so those are the different hyperparameter we can change. And to see which one we are going to use, let's dig into the report again. So max steering, we see if we limit the action space, well, it will also normally learn faster. The throttle limits, again, if we here is the default one. It's the one where we allow to brake more and to also go slightly faster by not having the limits at the very limit of the action space. And here it's when we give even more freedom, so to allow the agent to completely go backward. It also learns slower because it needs to also explore the whole space, larger action space. And here there's a lot which is all about the going backward, which is not useful in our case. We may brake faster, but here it's not useful. So thanks Corey for so Corey's going. Thanks. Yeah, you will see the replay. And okay, so that's one thing. The other thing that you can change is the max cross-track error, as we see. And here it's interesting to see different thing is if we set it to 8, so which is kind of the normal width of the track, it will learn, but it will be capped in terms of max lap time you can achieve. Here it will be around 20, but on the other side it will be also very robust, so it will almost never crash. Like if you compare the length of the episode, this is this run. So 0.8. So the length will be quite quite high compared to the other experiment. And maybe before I tell you, and so the other max cross-track error, so you have a sweet spot, because if you do not penalize it at all, it will just try to go as fast as possible. And it will not learn to it will just learn to go fast and not go fast and a bit near the center of the line, and it will also hinder the lap time. And for that, in fact, we're going to go in the environment, again in Donkey Sim, search for calc reward, and see how is the reward defined. So the reward defined is we want to go close to the lane, so it's a squared error because we want to be close to the lane, but if it's not exactly 0, it's okay, because if you parent here, if the error is absolute error, then it will be penalized the same. If it's further away or closer to the lane, it will really enforce to be on the line, but here we want to be close to the line but not exactly on the line, so squared error is more appropriated. And this reward, so going close to the center of the line, is modulated by the speed. So we multiply it by the speed, so the normalized speed, and that's it. And we can also add other thing, which is if we are done, in fact, which means we are in a collision, we can also penalize it for going fast. If we go in collision. The same here, and let's penalize it even more. So it's really okay. The same here. Is there any question about the reward function? So the reward function is quite simple. We penalize it every time we hit or we terminate the episode, which is if our cross-track error is too big or if we have a collision with the environment. And then otherwise we just go fast and be close enough to the lane, and the close enough will be modulated by that max cross-track error. So we can be more lenient by allowing the agent to be further away from it. But it will give it a very nice feedback that going near the center line is actually good for finishing episodes. So Altex, I've got a small question. If I want to change a car camera position, can I use the same autoencoder or should I retrain it again with a new data set? You should probably need to retrain, but you can maybe, instead of retraining from scratch, reuse the previous weights as a starting point, so you waste less time training. Any other question? Why we set the max result to 1.5 while the real max is 1? Yeah, that's a good question. So it's a trick. I'm not 100% sure it works all the time, but the thing is, because the way the RL algorithm works is in its output, it squashes its output between -1 and 1 and then rescale by what we want. And it squashes it using a hyperbolic tangent, which makes it less likely to be at the very limit of the action space. So if we put the limits further away, then it will be more likely to actually sample or output 1, so the maximum speed, instead of outputting something like 0.9 or 0.99. Does that answer your question, I hope? Okay, perfect. So what we did is mainly normalize the reward. So normalizing reward is very important, especially when you have several terms in your reward, because then it's easier to weight each term of the reward. Okay. So what we have seen is, so max cross-track error, there's a sweet spot. So if we are too lenient, it just learns to speed and it's okay, but it learns slower. So it actually can go faster than if we set the max cross-track error to 8, but it will take more time. And if we are too restrictive, then it will just go around the center of line and don't do any racing line. I won't go too much into the continuity cost. Continuity cost is very important if you are on the real robot, because you want your output to be smooth. But here, because we are also trying to maximize the speed, it will indirectly maximize also the smoothness of the output, because if the steering is going back and forth, it will also slow down the car. So by maximizing the speed, it will also enforce the continuity. Then one interesting factor is the gamma, so the discount factor, which is telling you, should I optimize for immediate rewards or long-term rewards? So long-term rewards will actually is the one that actually gave me the best result, but it needs more time to train, because it will need to usually, so here what you can see, it takes longer to train, because the horizon is also much further. And if you have a smaller discount factor, it will learn faster, but then it will be capped, because it will just optimize the immediate rewards, and the immediate rewards, it's not about doing the full lap, full speed. It's just about doing the small portion of circuit close to it full speed. And then you have the in-between, which is usually a good default, 0.99. And this is what we are using currently, but we could also change it to 0.995. Okay, so let's go to, and then I won't go into that. And then the last thing we can change, we can change the algorithm, but I don't have any data yet, is the network size. So if it's too small, it won't learn, and if it's too big, the thing, it will be too slow to learn. And because we are learning in parallel, you need to tune how often do you train, and this is it's called train frequency, and how many gradient step do you take, which is the gradient step parameter. It's where you need to have a compromise, because if it's too big, it will be too slow to train, and it won't be in terms of wall clock time, it will be the same time for training. So usually having a medium-sized network is a good compromise between the two. Okay, so let's see and go back to our training. So we see that max cross-track error should be, in fact, bigger. We saw that our discount factor, let's see our discount factor here. So if we want to be really fast at the end, let me check also how long does it take. If you go to global step and replace it by relative time, here it takes 2 hours to be under 20, but then it also reaches lower lap time. So we will keep the default one, but we can still pass it as a parameter. So here gamma, we can set it to 0.99, which is the default, and we could change the same way we could change other hyperparameter directly in the command line. And all those parameters that you pass here will be actually saved, and when you test your algorithm, then that's what we're going to see also next. Then it will be automatically loaded, especially the limits, because sometimes you test things and you forget, but the zoo is directly saving it for you, and you can also access them in the weight and basis. So let's just start training, and then we can keep talking while it's training. And again, the simulator, you can change the simulator speed, so how fast the real-time factor is. If the real-time factor is in fact too high, then the problem is it will collect data more rapidly than the callback. The training parallel callback can do gradient updates, and you will have usually you try to do as many gradient steps as you collect data, and that's what you can see here. It's the number of updates. It should be more or less of the same order of magnitude than total time step. Otherwise, it just means that you are you are not using all the samples that you are collecting for updating your policy. And here, actually, it seems that the car name was discarded somehow. Maybe that's not the correct name, but we can see that later on. If we go to Donkey Sim, car name, okay, no, should have been okay. I don't know, it didn't take it into account, so I'm a bit... Car config, car name test, I don't know. If someone knows why it didn't work, I'm happy to learn about that. Okay, let's just check actually that the limits are the right ones. So lap time. So, and now we have our second run that we can again see in Donkey Live, and we can compare them later. But I'm just a bit afraid that this is not using the correct environment. Let's just be output here. Set cut. Oh, actually, we don't set the CAC. Okay, I see. Send config. No, okay. Let's just check that the config is passed, and we don't need to track anything for that. but we're going to pass a TensorBoard log, just so it doesn't crash. Okay, so normally we can access self.config, and here we have everything: car config, car name, RL test. So it should work. So I'm using IPython debugger to quickly investigate or be in the code and debug directly in it without having just to print things. And car config. Yeah, it's the correct name. Okay. Ah, okay. Yeah, we need to have a body style in it. All right. So here, if we want our car name to be display, we need to specify a body style. So body style is just how our car look like, and for instance, we can make it look like a Formula One. But for normal training, let's just make it a donkey, and we can also change the color and be, I don't know, it's body RGB, it's called body RGB, and for instance we can make it all black, so 0, 0, 0. And we are tracking the experiment and everything is saved. Oh, and yeah, and now we need to set the font size too. So once you specify the car name, you need to specify all the config, otherwise it will complain. Font size, let's say 16. So body style, body RGB, car name, font size. Okay, we should be good to go. So yeah, IPython debugger is very useful and prevents you from just printing things, and you can directly. So that's what we have. We have now a black car with our small name on top of it. Okay, so while it's training, we can actually, so here we have many runs. This one we can actually discard 10 seconds. And this one, the last one, we're going to call it DonkeyCar and tuned parameters. Tuned parameters. And we hope that it will be actually, normally it should be actually faster than the other one. Okay, and so you can, again, if you look at in the chat, I can repost it for people that were not there before. You can access it and see it live. So it's in DonkeyCar, Donkey Live. Yes, I will repost it in the chat. And I will just also put more music. So I'm using Polymos, which is my brother YouTube channel for music, quite nice music. All right, so I will also go back here to see how it's going. So quickly, after some time, it will learn to do a first lap, and as soon as it does a first lap, then it will do more and more laps. Here, it's the mean episode length. Here, it's the mean reward. The thing is, because our reward is only a proxy, we don't really want to maximize. We want to maximize that reward, but in fact, the policies that give you the max reward is not necessarily the one that gives you the best lap time, because that's not what we encoded in our reward. In fact, the one that gives you the highest reward per episode is the one that just keep running on the track without colliding on anything. But we want our car to take some risks, so yeah. And let's just check. Yeah, I think in terms of FPS, normally it should be, at some point it should be around 80 because it's 4 times faster than the normal FPS, and the normal FPS is around 20 for this environment. Okay, so yeah, we can see it train live. We can remove that one. And also tell me if the sound is too loud or not. Yeah, and my brother, so Polymorph, which is also in the chat, has a Twitch channel, and you can, of course, subscribe to him. All right, so the next steps now. So we will wait a bit while it's training, and I will explain how do we actually, once we have trained a model, how do we actually use it, and maybe package it into a Docker. Music is too low. Yeah, I can make it slightly louder. Here. Okay. But I mean yeah, music should be subtitled too. Okay. So, is there any question about what's next? Yeah. So one important thing maybe to note is that what you see here, the training lap time, which will also, yeah, we're going to do a running average on, I don't know, 20 runs, so that it's smooth. Actually, it doesn't have too much spikes, and it's easier to read if it actually improves or not. So this lap time during training, because we had some noise, we had some exploration noise, will be always lower than the real. It will underestimate the real performance of the agent. So, for instance, if at the end our agent is around 19, usually it means that it's able to do sub 19 laps. Okay, so let's just check that actually the hyperparameter app has with the right one. So here you can see it can do half the lap, well, sometimes. And the next steps we are going to do is actually, once we have trained one agent, we would like to export it and be able to use it for racing, because here the training code, we cannot use it for racing because it has all those automatic reset. And we would like to avoid that, and it has, we would like also to probably load the best checkpoint. So for that, if you go in the environment again, I will also close it. In Donkey Sim, in I think it's called determine episode over. You can actually see here it's the different condition for stopping an episode. So one is if we are above the max cross-track error. One is if we collide, and there's others that are actually not used anymore. And the first thing you need to do is actually disable reset if you are racing. And for that, you can just set the environment variable race to be true. And that's what we're going to do, is actually prepare the Angel script here. So we go where we are. So in racing live 2, in the zoo, we re-export the path to the autoencoder, otherwise it won't work. And what we are going to call is the Enjoy script. The algorithm is TQC. The environment is still the same, so it's still DonkeyCar multi-track. We're going to load it from the log folder. And here, what we can do is load say which experiment we want to load. 0 is the last one. And in our case here, this one will be this experiment. It says to you, it will be experiment number 34. 34. In fact, we're going to use the previous one, so 33. And then, if you do that, it will just load the last model and try to run it. So as we say, we want to race, so we just say race equal true as an environment variable, so it will disable reset. And we want to, if you want to load a checkpoint, you write load checkpoint and then the name of the checkpoint. If we go in here, and so we go in the zoo, in the logs where all our trained agent are, and so we're going to choose the previous, the previous successful experiment is in fact 30, yeah, it's 28 because we did some runs that were not successful. It's 28, it's 28. Here in the config file, what we're going to do is remove the time limit. So we go in the config, we have the time limit here and we remove it. And that's mainly all what we need to do because normalization is here. It will be loaded automatically again. And the time and the checkpoints, so the checkpoint, we have different checkpoints and we could load, for instance, the last checkpoint, which is 125,000. So 125,000. And this allows you, in fact, to check different checkpoints to see the performance of the different ones. And also to see, it allows you also to see the how it improves over time or not by loading different checkpoints. So if I launch it right now, what will happen? It will launch a second car on the screen. And this checkpoint does not exist because I did 10 too many. So here you have a second car which appear and which can start to also race right now at the same time. And we're going to stop it. So here it will also tell you what is the best lap time and we can stop it. So that's how we do. We search for the experiment we want. We can go in fact to weight and biases and search for here, if you go to global step, for the time step where the lap time is the lowest one, and then use that one. Okay. Yeah, and so currently the one with the highest limit, so with -1 and 1 limits, learn faster, but it will usually be capped quickly because with a higher limit it managed to avoid the ramps and things, but then it will be capped in terms of how fast it can do a lap. Okay, and maybe the other thing I would like to show is how do you, once you have the race here, how do you put everything in the Docker? So the good news for you is I already have Docker ready, and in fact I can here send it to you. If you want to test home, you can directly use my model with Docker. So Docker is mainly, here we go. Okay. So, and it uses, so the name of, yeah, so the name, here we go. So here we can see that after some laps, some slow laps at 35, it quickly starts to pull better and better laps. So this Docker image is, we can in fact start it and go inside it. So we can just do Docker run So Docker run interactive mode, we remove it after playing with it. And we use bash, we have bash, let me put it right here, okay. And we want to be inside it with bash. So in it, if all the important thing is in code, /code, no, /root/code. And what's inside is exactly what I used today. So the autoencoder code, the Jim DonkeyCar code, and the RLZoo code. And I also put the autoencoder model in it. If you want to use your own model, what you need to do is actually go inside it, pull the latest version, and also check out the correct branch here. So let's see which branch we have. It's fetch tweet 3, which is probably not pushed. Check out the correct branch, and once you've done that, you open another terminal outside your the Docker, and you can go Docker document. Let's say, oh yeah, it's in here. We have our autoencoder. We can just do Docker cp for copy. What do we want to copy? We want to copy the autoencoder, and then the name of the current container is Igor Gagarin. And then we put it in /root/code. Here we go. And now if we do ls, we can see it's here. And once you have done that, you do the same again for the models. So you need to put it in the RLZoo, in the logs, So if you go to RLZoo and you see in the logs in TQC, you have the different run that you want to use at the end, log TQC. Here I will need to copy, in fact, I will need to copy the log folder which contain my model. So in my case, it's in, I can, in fact, document RL racing car live2 and RLZoo, and here it's in log TQC. We have the same structure, and we just need to copy one of them inside. So in my case, I will need to copy one of them and do that. Once you copy it, I won't do it. You can do docker commit. Docker commit with two things. One thing is the name of the current container, active container, and then here you need to replace it with your own user space and an own tag for the image. And once you have done that, then you can use mostly the script I sent for that. Okay, so now we can see that it's already pulling laps below 25 seconds. After only barely 15 minutes of training, not even 15 minutes of training, which is quite nice. And we can now compare, in fact, start comparing the two. Here we go. We edit the panel and we will compare on, in fact, 40 lap time. You can see it's that the tuned parameter is quickly starting to catch up with the untuned parameters, and I will also put it slider limit, maybe 30. Yes. Okay. So it started to learn slower, but then it will soon catch up, and with tuned hyperparameters, it will in 1 hour it should reach 20 seconds. All right, so that's what we have. So once we have everything in the Docker, we commit it, and then we can use it using the script I sent you. And this script, I can in fact open it here, sub test. No, it's run. Not the right one. .sh. Let's make it bigger and wrap. Okay. Okay. Normally you should be able to see it, even with my face. Good. So what this Docker is actually doing is just running everything we do locally, but inside the Docker, so it's easier to ship it to the server, because when you race, you can actually ask for having Docker images and to Altex, and then run it without any delays on there. And in fact, so the command line is mainly just the command line for the zoo. So it's the Python enjoy script that we use so far. With n being the number for how many time steps do we want to run, we just need a number big enough so that it doesn't stop during the race. It needs the X ID, and we pass different parameters. So this one is to use only one CPU, because it's usually a little faster, and we can pass different arguments like for the race or things. And then it just run into the Docker image. It goes in the RLZoo and run our command line. So do you have a script to release a Docker container from scratch? Yes, so to create a Docker container from scratch, in fact, I'm using the one, if you go to SB3RL, so in Stable Design 3 and also in the RLZoo. In the RLZoo, you have a Docker and Docker file, and in Stable Design 3, in scripts, you have also, here, you have a Docker file. So this Docker file of Stable Design 3 gives you the basics, Python, so Conda, Anaconda, and I think it installs also PyTorch, and this script is available for both CPU and GPU. This is a very basic, and you can in fact add more here, the different steps for installing or creating your environment. But in fact, you're right, I should probably add the full Docker file, but for this RL thing. And the zoo is basically based on the stable baseline image, and it has additional dependencies. But yeah, and it has also a hack to be able to run things that requires X window. But of course, Altex, if you start from the stable baseline 3 Docker file and create one that works with everything I've shown so far, I would be very happy to share with other people. It should not be too hard to modify, because you mostly need here to do a pip install of the different repo I've shown so far, and to do a Docker CP copy here of the autoencoder, a copy also of the model maybe. All right. So here, after almost half an hour, I think, of training, so we are around 22 in terms of, yeah. So here again, those labs, the true model, not the true model, the deterministic one, or the one at test time, will actually do labs which are faster than those one. But it's actually already quite nice. It's doing several labs without crashing, and it's doing it. It's racing, so it's still wiggling a lot, and that's what is going to improve over time, which is being smoother and being faster. So I think I've shown you at least, yeah, okay, now it's getting faster and faster, everything I wanted to show you, and I could just leave it training while showing also the best lap time next to it. Do you know any optimization to be able to run a car from a different start position. I don't do any optimization to be able to run the car from different start position. I didn't know it could be started from different start position, but I don't do it. I should do it if the car was not able to finish a lap, but in fact it's learning to finish a lap quite quickly, so I don't need to do that, because it will explore all the environment more or less the same, because, well, more the start, because usually it's restart at the beginning, but soon it will do enough lap to have enough diverse experience. But of course, if it doesn't manage to do the very end of a track, then you probably need to restart it, or to have some hand-coded policy or something to be able to not start from scratch. When I run two cars for a race. The start position. No. So actually the good news, so the question of Altex is whether I can I do different optimization for starting on the right of the start track or on the left. I don't do anything because it has learned so it doesn't learn to start from the left position, but it has seen something similar during training, and it can cope with that without a problem. Okay, so yeah, now we are starting to be below 22 seconds in terms of lap time, and you can again follow it live if you want to. And we can also take a look at two things, which is first lap time and the second lap time. But for that, we need to edit that a bit, do some smoothing on, let's say, 40 runs. Same for the best first lap time. Here, so the first lap is around 23. If you see it, let's put it a maximum 18. Is around 23, and the second lap time now is below 22 already. And it's getting even more below. And everything is after, let's say, what's the wall clock time? Yeah, it's just 30 minutes. In just 30 minutes, we're already at 21 something. You mentioned that n updates should be at the same order of total time step. In the case of n updates are below, where would you change the update sit more time? Okay, so to answer that question, let's go to our hyperparameters. So in our callback, we define how many gradient steps we take and how often do we take them. Here it's a bit special because it's a short circuit, the normal training, which is first collecting data and then training. Because everything is done in parallel, this is the actual value which is done. So what do we do? And in fact, what do we do? One thing is, instead of running it, the simulation 4 times faster, you just reduce the real-time factor to 2 or to 1. And usually it depends on your GPU. So I've got a good GPU, so I can run it 4 times and it still catch up in terms of training time. In the case it's not exactly the same, it's okay also still to have that. But basically the one thing I do is mainly changing the real-time factor of the simulator. And one other thing you can do is also having a smaller network or smaller batch size, because it will take less time to compute. And yes, and the other thing is also to have less gradient steps, so that everything is in sync, that this callback should terminate before the data collection is terminated. And let's go maybe quickly see in details how it looks like. So in callbacks, it's called parallel time callback. Basically what it does is once you have finished collecting data, it synchronizes the replay buffer with the one on the thread, on the training thread, and it starts the process that train, which is here. Train. It starts the thread. It starts training, and once it's ready, then we can continue training. And what you need to check is actually that this thread should terminate before you collect again data. And mainly what you can change is the number of gradient step, the batch size, the network architecture. But problem is if you make it too small, then it won't learn as fast neither, and the real-time factor. Okay, so we have our first lap below 21 seconds, which is quite nice. Are you using a PC or laptop right now? Right now I'm using a PC because it's, especially when I'm streaming, it's nice to have a GPU for that. But I used to use only my laptop for training. But with the laptop for training, it takes longer to do gradient steps, so I need to make everything smaller. So I hope I answered your question, Guix. All right. Okay. And we can plot it again, the lap time. Would be probably, yeah. Okay. All right. Any other question? Otherwise, I would just let it run. And see and cut it probably in 30 minutes. I think everyone is done. What is OMP num thread? That's a good question. So so the question here is about the test script I sent here. This is a standardized environment variable for the number of thread that is used for parallel operation when doing matrix multiplication. So it's used by PyTorch, for instance, but it's used also for, I think, by NumPy. And by default, I think it's set to your number of CPU, or it has some heuristic for that. The problem is because we are using only a batch size of 1. If we use multiple thread for matrix multiplication, there will be a additional cost, so a overhead cost of launching the threads and doing the computation that is slower than just using one CPU. So this one is enforcing that we are using one CPU. In fact, in the zoo, you could also directly set it using num threads and say it's 1. But using this one is a bit more general because I think NumPy is also using it. So if you go to PyTorch and num threads, you will find some documentation about what it is. All right. So now we are doing laps under 21 second in a consistent manner. And let's just wait, 30 seconds, and then we will kill it and we'll see how we actually use it for in practice. What's the next plan for the next presentation? Well, it depends on you, I would say. It depends on what people want to see or want to try out. Maybe I could get more into Docker or talk more about our algorithms or other optimization. Or we can also just do a quick recap of everything and try to do in only 1 hour from scratch. So collecting data, training the autoencoder, and starting training RL all in one go on a new track, and we could decide the track we want to use. So because all I've shown you so far is independent of the track. the same process can be applied to any track. Does it make sense to buy a gaming laptop for such thing, or rather something like a ThinkPad P series? I don't know ThinkPad P series, but usually what's needed, so for when you do simulation, what's needed is a good CPU. And for reinforcement learning, okay, GPU is fine, but a GPU that is CUDA enabled is always a nice thing to have. So I don't know what is ThinkPad P series, what they look like. Yeah, but if you want to, a gaming laptop will probably have the GPU needed for that. Okay, let me just check quickly. So here, if we go again to our dashboard, and we can compare the different metric, so we can see that in terms of episode length, which tells you more or less how often do your agent crash, the model caught up with the previous one. The mean reward also, so we are also doing better than this one. And then, well, you have the GPU power usage, but that doesn't matter. What matter here is different things you need to check. Is the critic loss. Critic loss is your value function estimation, so estimating how good you're going to be, and this will in fact in the beginning start to grow. It's normal because you will discover new rewards, new states, and it will be unprecise, and then it should start to decrease slowly. The standard deviation should also decrease over time because it tells you how much you explore. And then let's see if there's any other things I can talk about. Actor loss doesn't mean much, in fact. It's a very just abstract loss function, in fact. And the entropy coef is also telling you how much you are more or less exploring. The two should be linked, so the standard deviation and the entropy coef should be linked too. And the FPS allow you to actually check that everything is running as fast as you expect. So here we are around 70 FPS, which is almost the 4 times factor that we expect by running the simulator at 4 times the normal speed. Okay, so we have trained for 35 minutes now. If we look at the second lap time, we are around 20.5. So this is during train time. So at test time, you will see it will be slightly faster. So 20.5. You can even have the log. If you go in here, you can even access the log terminal and have all the metrics here. Okay. And the first lap time, so the first lap is around, let's see if it loads. First lap is probably around 22, looking at the logs, yeah. Let's see. And the other thing is when you will test your agent, you usually test it at a lower real-time factor because it will also go faster because there's less imprecision in the computation. Okay, and the first lap time is around is a bit lower than 22. So let's see, in 35 minutes, let's kill it now. And let's do what I said. So it will synchronize with weight and biases, and you can check out later how things are going. Okay, it has synchronized things. Also, if you want, that's something I didn't do, but if you want to continue training, you should do save replay buffer here. Okay, there's a lot here we don't need anymore because it will be loaded automatically. So we're just going to clean everything. So we want to race, so race equal true. We're going to call the enjoy script on the key TQC algorithm. The environment is DonkeyCar. The log folder is log, and the experiment ID is the last one. And we want to run for long enough, so we just put enough timestamp. And let's see. So I said about a bit below 22 and a bit below 21 for the second lap. Why is the FPS less than 80? Because we have some sleep time I didn't take into account at reset. Oh, actually it's below 20 already. And we see that here the first lap is actually quite much faster than what we have in our logs, because here we are not using a stochastic policy anymore. We are using a deterministic controller, so there's no more noise added to its output. And we can see, yeah, it's running quite fast. Let's just kill it and set the timescale to 2 only and not 4. So it should even run faster with timescale. Okay. So I think, yeah, it should be around 21.1 probably, and the other labs should be around 20. So the bottleneck is not CPU, GPU. The bottleneck is actually there's some sleep time, because when you reset the car, you don't want it to run directly. And all the reset process is in fact costing some time. And that's mainly where you see some drop in FPS. But at the end, when it gets better and better, you will be closer to 80 FPS. So here we see, just by training while I was talking, we are already racing and around 20 seconds. So next things I would like to do is try also the different checkpoints to see how faster we got. And so we go to our logs, to config, and I will terminate. We remove the time limit because we don't want it, it's racing now, so we don't need time limits anymore. And we see the different checkpoints that are available, and let's see a checkpoint that is further away. So we stopped at 150,000. Let's see if we stopped much before. So 1, 2, 3, 4, 5. How fast we would have got in between those checkpoints. And the idea here is, usually you will take a look at your logs and the training curve and see what model should perform best and try different checkpoints. But usually the one that is trained at last is the best one. So here we see that earlier model, it's slower, it still complete the track. But it will probably also crash at some point. And we can even, yeah, so it's much slower than the one we have. And the nice thing is, in case you want to compare different model, really, you can just open another terminal, go where we are, racing RL2, live2, RL2. Don't forget to export the path to the autoencoder. And here we're going to make it race against the last checkpoint. Oh, and we want to be able to compare them. So I'm just going to copy here, car config here. We want to compare them, so we pass keyword argument as keyword argument. That may not work. Let's see. We want the conf to be addict. We pass a config, and here the main thing we're going to change is last checkpoint. This may not work because, okay, this worked. Yeah, this may not work because we need to pass the complete config. But let's see. Let's kill it because this one is not working anymore. This was a Docker image. But still, we will make the two race. And I mean, so the one on the the left is the oldest checkpoint, and the one on the right should be the newer model. And by doing so, in fact, you can compare different models quickly. So in fact, oh no, the model on the left is the last checkpoint, and the model on the right is a previous checkpoint. So by doing so, you can compare different models. And here we forgot something, which is putting enough time step. And this name and the color, you can also change it. That's what we're going to change, in fact. In the config, here in arguments, you can directly, let's change to white, 255, 255, and 255. And let's call it last checkpoint. Okay. Now we can actually see the two. And once we have the two, we can make them race together. And that's it. So for comparing models, usually I first do checkpoint alone, and then I compare the models by doing some race once again the other, and starting from one pose to the other pose. So to answer your question, Altex, as you see, it was never trained to start on the left, but it still managed to do it. And here you can see in the log, so the last checkpoint is doing laps under 20 or around 20, and the other one is actually crashing and doing things above it. And just for fun, let's just compare it to the model I used for racing this Saturday. Let's do a small race. And the one I used has much more training. It has several hours of training, I think, 10 hours. And let's just make them race. Yeah, it's a bit brutal. Okay, let's make it a little slower. And what's gonna happen, I will probably also start my model on the right, so it can actually go faster. Okay, so let's start this model on the right and this model on the left. So there's no more, and we can actually race. Okay, so here we are comparing the model we train here on the right, that we trained during this live, to the model that was trained for the race during several hours. And to make it maybe a bit better, let's make it a time scale of 2, so it's faster to see when they take over each other. But what's going to happen is this one is racing much faster, and that's what we're going to see in the logs. So here the first lap of the first one is around 20 seconds. Here, where the first lap of the other one is around 22 seconds. So it's already far away, and we're probably going to fast forward everything, because so it's doing laps around 18.5, where the other one is doing laps around 20 something. So it will probably catch up quickly. Yes. Okay. And also, more than catch up quickly, it will just crash at some point. And I did not implement, which is any recovery strategy, which is the case for the one on the left. There's a very basic recovery strategy. Okay, so thank you for watching. Last question is now. I will just finish this live with the 2 car racing, and probably one of the 2 crashing. And also, if you have ideas about what to do next for the next live, would be interesting. And here we go. Okay. So thanks for watching. I hope you will try it at home. And of course, everything I've shown here is open source, as is online, especially this all those runs and this report. I will put a link probably if needed. And yeah, so thanks for watching. Bye bye.